Okay, good morning everyone. This is Gajendra Shekhawat from the Spirit Nuance facility. So I will talk pretty quickly, about the Nanoscale IR system that we have installed late last year in the facility. It's a combination of both Nanoscale IR and Photothermal IR. Basically, they are the same technique but two different names. So a lot of people ask me that can we do photothermal, can we do nano IR? So I think this would clarify uh, that there's no difference. So I will briefly start, with the importance that how there's advancement in the AFM technologies. You can see long time ago in 1980s, how the AFM looks like. You see in the picture a few wires, connected together. They put together a probe and then a sample. They try to physically touch the probe through some nanomanipulation techniques. And then out of that, they created basically scanning tunneling microscopes. It's basically handmade. And then they generated, they just took a graphene monolayer out of through a scotch tape, and then they image those hexagonal lattice. So that shows that the fundamental principle of that technique to resolve things at atomic scale, and then that really developed into a very sophisticated AFM type imaging tool later on. But now, as the technology advances, AFM is no longer just simply a surface measurement tool or just doing a surface topography or reference measurements. AFM advancement went deep into the more kind of a functional imaging where you can correlate topographical variations, and then you can get a topography images, but you can also get different functional images, like you can do electrical properties, magnetic properties, optical properties, photothermal properties. Now you can also do these uh, nano IR. Basically, you can do these chemical properties. Okay, so there's a great advancement in these techniques as well as the regulation. So this allows people to do multiple options on the same tool. Okay, so this is that system in the museum sitting there in the Museum of London. And then if you go there, you can see that this is the first scanning tunneling microscopes. It looks like, a space shuttle. Okay, so since this is different types of instruments, techniques in the scanning probe microscopy facility. We have a bunch of AFMs that can do mostly the functional imaging. Whatever the capabilities are there in the AFM that exist today, we can do it here. We also have a Raman spectroscopy, and then we have integrated that system. It's also the AFM, so you can do tip-enhanced Raman spectroscopy. You can do down to the resolution of 1 or 2 nanometer. Okay, then we have nanomechanical system, we have nano patterning systems. So these are wide range of systems that we provide to the users of our facility. Okay, so people are very familiar with this FTIR type imaging spectroscopy that is pretty conventional. People use it all the time, and we have one in the Keck facility here, but it offers chemical information, but it has a very limited spatial resolution. Okay, but then it has a broad range of application, both biological, chemical, physical type of techniques. And then these are the common chemical functionalities that we can detect with IR spectroscopy. So depending on what type of laser we have, the current laser we have is basically go from anywhere 700 wave number to 1800 wave number. So mostly you can cover all those single bonds, double bonds, amide, DNA, proteins. So most of the chemical fingerprinting happens within that range. And then, time, place, circumstances we needed, we can add another laser later on in the coming years, so we can widen the detection range. But most of the things that people usually come here to detect these chemical compositions falls within the wave number of the laser we have. And then you can see the atomic force microscope world. You can see these different techniques. You can do thermo, electrochemical. You can also fabricate with the AFMs like nanopatterning techniques. You can do mechanical, electrical. So AFM is mostly is widening to the different technology areas, and and then single tool can do multiple things. So why we want to do nano IR? Because it is a combination of both IR spectroscopy and atomic force microscopy. AFM provide a pretty high resolution because of the size of the probe, but it doesn't provide any chemical identification. So we have to integrate with the IR spectroscopy, which provide the chemical information. And standalone IR spectroscopy cannot give you the resolution that you need, but if you combine or integrate these two techniques, then we can have the information about the AFM, you can have information about the chemical imaging, and you can also get the resolution what you want, which can be few nanometer. Okay, so there are different ways to beat this optical diffraction limit with the AFM. There are different techniques. AFM obviously it's not falls in the category of this diffraction limit. It uses a mechanical detection. There's a base method. You have basically a piezo scanner. You have a detectors, and then how the laser reflects from the probe and goes to the detectors. It's all mechanical path that can give you down to few nanometer resolution. And then we also have like a similar setup like a scanning near field optical microscope, where you can get a very high resolution optical images. If somebody wants to study plasmonics and all those things, they can do with S-norm. We don't have that technique, but the whole concept here is that how you can approach the nano IR, basically detect the signals in a pretty close proximity to the samples. Okay, so photothermal AFM-IR, which is also called the nano IR, is mostly used for chemical identification and functional group, on these materials. And then the scattering S-norm it can use hard and soft material, mostly used for study plasmonic and other optical related properties. Now, what is the operating principle? So you can see here the operating principle of this. Basically, it uses a laser, okay, and the standard AFM setup. You have a cantilever, so when the pulse arrives at the samples, it heats up and expands, okay, and then as soon as the pulse arrives, you do that process. At the end of each pulse, the sample relaxes back to the equilibrium. When the pulse comes back again, the process repeats. So this is how you can generate the thermal expansion within that small volume, okay? And then the pulse are tuned to a cantilever resonance, which causes it to ring, okay? This program has already been programmed through a software. So basically it excites the cantilever resonance, and then the magnitude of this ringing, the amplitude is proportional to the thermal expansion of that particular small volume under the probe. Okay, and then we measure this response as a function of a wave number, and then the amplitude corresponds to the IR spectrum. So this is how the principle of this technique works. It's a pretty straightforward. And then first step, as you have seen in the video, IR pulse comes at the sample surface, sample absorbs the pulse, heats up and expands, and then it applies the mechanical force in the AFM probe, because the AFM probe is basically in a close proximity to the sample surface. Okay, it's mechanically coupled, and then you measure the response. So the magnitude of this force is proportional to the absorption coefficient. Okay, so you you do the IR spectrum, but at the same time you use the AFM for high resolution. And then this is another way you explain FTR data. So this slide I will skip. It just shows that how much absorption power you have depending on what is the pulse rate of the laser. And so you can access the true chemical selectivity. Okay. So it's a Bruker patented technology, and then basically it's well understood. The theory, the principle is well established, and people, a lot of groups have started publishing the data from such techniques. So wherever you get the peaks, so there is also a data table like know it all FTR database where you can find out what specific peak correspond to what specific molecule. So these are already there. But if you look at the broader scale identification methods, there are various methods that can give you the elemental information, chemical information. So this is like a broader picture. So you can see here the nano IR fall is within 1 to 10 nanometer. So mostly you can do the chemical bonding and molecular or structural information with these techniques. So there's always this slide shows that sometimes you operate this cantilever to resonance, and then what happens depends on the sample elastic properties. Some samples are soft, some samples are hard. So what that means when the cantilever interacts with the sample surface, based on the density variation, there is a shift in the frequency of that uh, cantilever. Okay, the shift in the frequency, so the contrast will degrade over a period of time. Okay, and then most of the shift happens because of the mechanical properties. But how we know that basically we are measuring the true mechanical properties or true chemical properties, because the contrast degrades with time. So there's a phase lock loop on this system. It's integrated. So what that means, it try to track the resonance. If there is a shift in the frequency, it try to put back on track so you will not lose the contrast. So you will get the true chemical contrast, you get the true mechanical contrast. There is no degradation over a period of time if somebody is scanning continuously. So sometimes the mechanical variation also need to be considered. So how you separate those things. So how this techniques works is basically uh, you let me skip this. So how this technique works is that you can do two things with this technique. One is you can do the spectroscopy. You keep the probe fixed in space and scan the IR wavelength. Okay, and then you can get a spectrum. And then the second thing is that if you identify the spectrum, you use that specific wave number of that spectrum, and then you can input into the imaging parameters, and you can do uh, the mapping. Okay, so you can have a simultaneous topography and IR chemical mapping. So the mapping, if you have a different specific wave numbers in a particular material, you can map them separately. Okay, and then you have a chemical mapping, and then you basically have the IR spectrum. So you can have both things. So there are different modes of operation. We have a resonance enhanced AFM-IR. This is a contact mode. So the whole idea resonance enhanced is basically you are exciting one of the cantilever resonance to enhance the signal. Mostly it's a contact-based technique. So if you have a very soft material, that might contaminate the probe. Then you have a surface sensitive where if you have a few monolayers, you can use that technique to do the surface sensitive chemical imaging. A tapping IR is the more popular, okay, because it is very useful for soft materials, hard materials, biological materials. Resolution is less than 5 nanometer. It doesn't provide any lateral forces, so sliding. So basically, it's pretty good for soft materials. We don't have the one in the end. And then the Bruker used to supply the earlier probes in a gel packs, so which is a PDMS. So obviously you can get a PDMS samples based on the feedback that we provided. Now they are sending these probes in these metal things, so at least the probe is not contaminated with any PDMS material, so you will not get at least that big. But some of the key applications is polymers, life science, pharmaceuticals, environmental materials, semiconductor, what to speak. So sample preparation is not an issue here. When it comes to nano IR, the Raman system, sample prep is pretty critical. But in this case here, preparation is not, because the laser is coming from the top, so sample thickness doesn't matter here. Okay, so but we cannot do things in liquid. So why modulus alone is not enough? So this slide shows the example. For example, if you look at the top things, you see the topography, then you have a modulus image, you have adhesion image, and then you can, in the modulus image, you can actually see there are different components that give you different contrast. Brighter contrast means higher modulus, darker contrast means lower modulus. We actually don't figure out, what type of features we are looking at. So the advantage with this nano IR is that you can do the modulus map, you can do the topography, but at the same time you can do the IR map at different wave frequencies. Then you can easily tell, the features that you are looking is either, styrene butadiene rubber with the silicate fillers or some other materials, butadiene, urethane, styrene, silicate. So you can easily identify by mapping at them at a different frequencies within the same sample. So you can have a mechanical map where, as I said, things are very unknown, but then you can have these chemical map that can easily tell us what type of materials you are actually scanning. Then, recycle. These are some examples, that IR applications. I will not go in this, but some of the biological applications are also there. You can see the examples of liposomes filled with, the drug, and then you can see with the drug, the red contrast in the center of that particle or the sphere is basically drug. It's encapsulated in the liposome. So you can see here with this IR technique that you can identify. So basically it has a therapeutic application as well. And then you can see, you can do the IR spectrum, so you can also do a drug loading quantification in polymeric nanoparticles. Okay, so you can optimize the drug doses. So the whole idea is that you have a pharma application, you have bio applications, you have semiconductor applications, and many physical applications. And then this is basically some geological materials. So you identify the different bonding structures based on the spectrum that you can get. You can see either silicon or oxygen bonds, or the carbon-carbon double bonds, whatever the different types of organic chemicals are present in these materials. So you can easily identify with these types of imaging techniques. Okay, so I think that was in the conclusion. I can say that this is a wonderful technique, and then it can be used for imaging. Okay, it can do nanoscale spectroscopy. It can do the chemical ID with direct correlation to FTIR, and you can also do the mapping using the Bruker, patented quick force technology, which has more control over forces. This system is available for usage in the SPID facility. We installed this system, started working late December, so the people are coming and using it, and is available. So if you need more information, you can always let us know. It's a pretty new technique, but it's a pretty powerful technique. So over the period of time, I think the information and the message will spread. And it's pretty easy to use. People who know how to use AFM, they can use this technique. Okay, thank you.